Okay. So let's pretend you don't know anything about vectors.
Pretend.
A vector is a quantity that has magnitude and direction. So in mathematics, the best way to represent a vector is like this, with an arrow. The length of the arrow is the magnitude, and the direction it's pointing is the direction. So let's call this vector v. Notice you gotta put the little thing over it, yeah? Or, if this is point A and this is point B, we can call this vector AB. It goes from A to B, because see how the tail is here and the head is there. Okay, then how do you multiply a vector by a constant? So if this is vector v, how would you draw 2 times vector v?
Double and length.
Yeah, you double it, but you make it point in the same direction, so it would look something like that, right? How would you draw negative 1/2 vector v?
Chop
The
it in
other
half.
direction, but half the length.
Yeah, it's gonna be half the length, but point in the opposite direction, so it looks something like that. And then how do you add vectors?
The
Tailhead.
yeah.
Okay, so for example, if this is vector A, and this is vector B, how do you add them?
Make the parallelogram.
Okay, so you put vector A here, and then you take the tail of vector B and put it at the head of A, like that. That's vector B. And then you draw a new vector from the tail of A to the head of B. That is the sum of A and B. Sometimes we call it the resultant, yeah? You do the parallelogram, but that's the same thing, right? If you make the parallelogram like this. Same thing. And then how do you subtract vectors? So if I ask you to draw vector A minus vector B, that's the same as vector A plus negative vector B. So you take vector A, which looks like this, and then you take negative vector B, which is points in the opposite direction. So this is A, this is negative vector B, you add them together, that's vector A minus vector B. Okay, but lots of times you really don't want to draw the vectors, right? So that's why we learned how to componentize vectors. So, in the Cartesian plane, okay, let's erase. Let's say that this is 2-dimensional, of course, then, right? If you have 2 points in the Cartesian plane, let's say like this is 1, 2, let's call this point A, and point B is 5, 5. Let's say we draw a vector that goes from A to B. How do you componentize vector AB?
4, 3.
Yeah,
And
4, 3. This means the x component is 4 and the y component is 3. It's just like you make a right triangle like this. This is the x component, that's the y component, right? It's like these 2 vectors add up to make this one here, right? So this one only has an x component of 4, and this one has a y component of 3. Or the easiest way to do it is just go head minus tail. 5 minus 1 will give you the x component, and then 5 minus 2 will give you the y component. And the reason why you have it in component form is then because it's so easy to do computations. Like, how do you find the length of vector AB? When you put the 2 bars around,
Square
it means
root.
the length. Yeah, it's simply the square root of the x component squared plus the y component squared, and you get 5. And that just comes from the Pythagorean theorem, right? And then when you're adding vectors, you don't even have to draw pictures anymore. Okay, let's say vector v, let's say vector u is, make up some numbers, 2, -1. And vector v is -1, 4. What if I ask you, what is vector u plus vector v? You don't need to draw the picture anymore. All you gotta do, add the x components.
1,
Then you add the y components.
3.
3. Finish. And then what is vector 2u minus 3 times vector v?
5, no.
Well, if
7.
this is vector u, what is 2u gonna be?
4, -2.
4, -2. To multiply a vector by a constant, you just multiply each component by the constant. What is -3v?
Negative, 3.
3, -12. And then if you just add the 2, you get
7, negative 14.
7, negative 14. And then on top of that, when it's in component form, you can visualize can you think, what does a vector look like if it has an x component of 7 and a y component of negative 14?
Something.
So like, if you pick a point, if I go 7 to the right and then 14 down, it would look something like that then, right? So you can kind of visualize, yeah? Now, this is vector u plus v, so what is u plus v magnitude? Square root of,
7 and
that's,
5.
what? Plus 3 squared, and that's equal to root 10.
Yeah. I was looking at the one below.
Okay, and then of course, once you have two-dimensional vectors down, then now we can do three-dimensional vectors. And that's what we're going to be doing in this course, is all three-dimensional vectors. So, now you have, instead of just the xy axes, you have the xyz axis. You see this before?
Isn't it usually?
No, this is the way it is. It's like this. You have the x, y, and then the z-axis comes out like this, right?
Yeah.
Okay? This is the positive z-axis, the negative z-axis goes the other way. But this is the way we draw it. It's like you're looking into the first octet, right? See, because the xy axis divides the plane into 4 quadrants, but if you add the z-axis in now, then it divides space into 8 octants. The first octant is right here where that piece of chalk is. Right there, all x, y, and z are positive, that's the first
Oh,
octant.
okay.
So what octant would it be if all 3 x, y, and z coordinates are negative?
The 5th.
8.
What?
Should be 8.
Okay, right here, x and y are negative, right? But you're on the opposite side of the board.
So be
1, 2, 3, 4, 5, 6, 7 would be octant 7.
Oh, so it's just, okay, alright.
Okay, and then, okay, so how do you, like, what if I ask you, plot the point 4, 3, 2? You go 4 on the x, 3 on the y, and 2 on the z, right there. But then the problem with that is it's difficult to see, huh? So then you draw the box, 4 by 3 by 2. You make a rectangular box. See, the dimension of this box is 4 by 3 by 2, and so that's the point 4, 3, 2. That's the way we draw it. Now, what if I ask you to draw a vector 4, 3, 2? See the difference between point and vector?
You can draw it back to the origin.
Yeah, so just draw a vector that goes from the origin to the point like that. See? It has an x component of 4, a y component of 3, and then a z component of 2. And then everything we learned in two dimensions is going to apply to this. Like, what if I were to ask you, okay, let's call this vector v. What is the length of vector v? It's going to be the square root of 4 squared plus 3 squared plus 2 squared. And then it does, and you can go to higher dimensions. Like if you have like a 4-dimensional vector, let's say vector w is equal to 1, 3, 2, 5. I mean, it's hard to imagine what it looks like, but then how do you find the length of it? It's going to be the square root of this squared plus this squared plus this squared plus this squared. So you can go to any dimensions you want. Yeah? And then adding vectors in 3 dimensions are the same, and subtracting and multiplying by a constant. So for example, if vector u is equal to 3, 1, 2, and vector v is equal to 1, negative 3, comma 4. How do you add these two vectors without drawing the picture?
Just straight down.
Yeah, you just add the x components, add the y components, and then the z components, and boom, there you go. It's so easy. That's why we have component form. And then multiplying by a constant, same thing. You just multiply each component by the constant. Okay, now we only talked about addition and subtraction, but what about multiplying vectors? Well, when you have vectors, there's 2 kinds of multiplication. You guys remember what they are?
Cross
Dot
product.
product and cross product.
Dot product and cross product. So the first one, the dot product. By definition, it's equal to the length of vector A times the length of vector B times the cosine of the angle formed by the two vectors if you put them tail to tail. So like this, what if vector A looks like this? This is vector A, vector B looks like this. Let's say the length of vector A is 3, let's call it 4, and the length of vector B is equal to 3, and that's a 60-degree angle right there. What would be the dot product of those two vectors?
12 cos 6.
It would be 4 times 3 times the cosine of 60 degrees, which is a half, and you get 6. And notice that this is a scalar, yeah? The dot product is a scalar, that's why some books call it the scalar product. And you guys all took physics already, right? So you know. When do we usually see the dot product in physics? Work!
Oh, yeah.
Are you guys taking AP Physics C?
I am.
Dude, I took B last year.
Okay, they didn't like. Work!
Yeah. 80, FNet.
Anyway, in terms of the work that we're gonna do, you use the dot product when you're trying to find an angle because of this. Okay, let me give you an example. Let's say we have a triangle in space. So here's point A. What are the coordinates? 2, 1, 3. Just make up numbers. Point B. 4, -2, 1. Point C. -1, 3, -2. Okay, which angle do you want to find? A, B, or C?
A.
Okay. So here's the angle we want to find. What two vectors make up that angle?
And you said
Vector AB and vector AC. So anytime you're trying to find an angle in 3 or higher dimensions, you want to use the dot product. Okay, so the first thing you do is componentize. What is vector AB? Componentize. You go head minus tail.
2, -3, -2.
Okay. And then what is vector AC in component form? Go head minus tail.
-3, 2, -5.
You gotta go head minus tail, otherwise your vector's pointing the wrong way. So now you just apply this definition right here. Oh, I forgot to tell you the theorem. Okay, before we move on. If two vectors are in component form, let's say vector A is in component form like this. A, B, C. And vector B is in component form. D, E, F. This is just 3 dimensions, but you can expand it to higher dimensions. Then to compute the dot product, all you do is you multiply the x components, you multiply the y components, you multiply the z components, and then you add them up. And that's why we want component form, because it's just way easier to work with. So that's a theorem. Okay, so the dot product of the two vectors. Now here are the two vectors. How do you find the dot product?
You multiply.
You multiply the x components, you multiply the y components, and you multiply the z components.
Yeah,
And then,
you divide by.
okay, we're trying to find the cosine of this angle, so what you do is you take this and divide it on this side. So if you divide that by the length of vector, the first vector, okay, how do you find the length of this
The
vector?
square root of.
Square root of this squared plus this squared plus this squared, so what is that? 4 plus 9 plus 4,
17.
root 17. And then the length of this vector is the square root of that squared plus that squared plus that squared, root
38.
38.
So,
That will equal to the cosine of this angle there. That just comes from the dot product definition. So it doesn't matter what dimensions you're in. You can be in 10 dimensions. That's how you find the angle. Just do this dot product thing.
Wait, sorry, so you said A times B is AD plus B equals CF. Why are we doing it over root
No, no,
17?
no.
we're solving for.
No, like here,
cosine
you take this thing.
Yeah.
What if you were to solve for cosine theta? You just divide this on this side,
Oh,
right? Like that.
alright, yeah, sounds good.
Like that. So you're just taking the definition and just playing with it,
And
right?
the absolute value bar is just.
That's not absolute, that means magnitude.
Magnitude, yeah, alright, that's
Magnitude. So this is the length of the first vector, and then this is the length of the second vector.
Alright,
Now, if this thing comes out nice, you can compute the angle. If it comes out ugly, then just say the angle is cosine inverse, whatever the ugly thing is, yeah? Okay, so that's the dot product. Okay, now we talked about the cross product. You're gonna see that a lot in this class. You're gonna see the cross product more than the dot product. Okay, you have two vectors. This is how we write the cross product. So that's why you don't say times now. You say either dot or cross, because there's two kinds of multiplication. And there's no such thing as division with vectors as well. Okay, by definition, so the difference between the two, the dot product will give you a scalar. It will just give you a number. Okay, just like you guys know work is a scalar quantity, right?
Yeah.
But the cross product is going to be a vector. That means it has length and magnitude. So first let's talk about the length. The length of the cross product is the length of the first vector times the length of the second vector times the sine of the angle between the two. And then you might know, well, hey, that looks like the formula for torque. Yeah, torque is a cross product, right? You guys took physics. Torque is a vector quantity, right?
Yeah.
Okay, example. Let's say vector A looks like this, and vector B looks like this. And let's say the angle between them is 30 degrees, and let's say the length of vector A is 3, and the length of vector B is 4. What would be the length of the cross product? Well, it's the length of the first vector times the length of the second vector times the sine of that angle,
So.
which is 1/2.
Yeah.
So you get 6. Okay, so now remember, the cross product is a vector. Here, I'll use this piece of chalk. It's a vector. So the length of the cross product will be 6 units long. Now we got to talk about the direction. The direction of the cross product is parallel, what am I saying parallel? Is perpendicular to the plane containing the two vectors using the right-hand rule. You guys learned the right-hand rule in physics, right?
Yeah, it's the.
Yeah, okay. Okay, now, A cross B, notice A comes first because the commutative property, A cross B is not equal to B cross A. Okay? A cross B, A comes first. So, the shortest way to go from A to B is this way, counterclockwise. So you take out your right hand and you curl your fingers like this counterclockwise. The direction that your thumb is pointing is the direction of the cross product. So if A looks like this and B looks like this, the cross product is pointing that way. And how do you draw a vector pointing that way? Like that. It's like the arrow coming straight out at you. So, if you were to cross these two vectors here, what is your answer? The answer would be it's 6 units long, pointing in that direction. You have to give the magnitude and the direction. What if the vectors were in this orientation though? What if vector A was here and vector B was there?
Maybe going into.
Then the shortest way to go from A to B is clockwise. So you take out your right hand and you curl your fingers in that direction like this. Because you cannot, see, you put your hand like this, you can't curl your fingers that way, right? So you have to turn your hand this way. Which way is your thumb pointing?
Into the.
That direction, right? Because it's always going to be perpendicular to the plane containing the vectors. So the way that we draw it is like that. That means the vector's pointing that way.
Which part?
Yeah.
So it doesn't matter if the plane is like straight up and down or
Yeah, it doesn't matter where the plane is.
the way you draw it, it'll still be just a dot or an X. Because like if it's
Well,
on a
we're not
plane, that's
gonna
square.
be, most of the time we're not drawing it.
Okay.
We're not drawing. Yeah, because the vectors, yeah, the plane can be like this,
Okay.
tilted, right?
Yeah.
Because you have any two vectors, if you put them tail to tail, they're gonna form a
Still
plane,
gonna look
right?
like that. Yeah.
They're gonna form a plane. Okay, but see, this is all dealing with pictures. But how do you compute the cross product if you just give it component form? So here's a theorem. If vector A is ABC, these are the x, y, and z components, and vector B is D, E, F, then to compute the cross product, Chad, do you remember?
Nope.
You compute a 3x3 determinant. I, J, K across the top. You put the components of the first vector there, then you put the components of the second vector there, and then that determinant will give you the cross product.
Be great if I remembered.
Okay, let's review how to compute 3x3 determinants. Oh my gosh.
That's.
Let's say vector u is, I don't know, 2, 3, 4. And let's say vector v is, I don't know, 3, 2, 1. How do you compute vector u cross vector v? So So you make a 3 by 3 determinant. I, J, K across, first of all, before we even go on, do we even remember what I, J, K is?
It's the thing that you put in a vector.
Okay, you know when you have a vector here, let's say vector V is, I don't know, 3, 2, 1.
The I, J, and K are all omitted, right?
Another way of writing this would just be 3i plus 2j plus 1k. It's just the coefficient of I is the x component, the coefficient of j is the y component, and the coefficient of k is the z. These are just two different ways of writing a vector in component form. Okay, so now you have to put this one in first now. Whichever vector comes first, you have to put the components here. Whatever vector comes second, you got to put them there. Because if you switch it, you guys remember what happens when you switch two rows in a determinant? It negates the value, so your vector is going to be pointing the wrong direction. Okay, now, we forgot how to compute 3 by 3 determinants. Select any row or any column. Okay, I'm going to go across the first row. Then you multiply each element in that row by its cofactor. So starting with this, I, how do you obtain the cofactor? You cross out the row and the column that it's in. And when you have a 2 by 2, you guys remember how to compute the determinant of 2 by 2?
A times
You go
B
this
minus
times this
B
minus
times
that times that, right? Always start with the upper left hand corner.
-5.
So 3 times 1 minus 4 times 2 is
-5.
-5. There you go.
Oh, okay, it's coming back.
Then you move to the next one, except it's going to be minus j because it's in the negative position, right?
Yeah.
Remember? Plus minus
Yeah.
plus.
Yeah.
Okay, so you cross out the row and column that it's in, and what's
2
left?
minus
2 minus 12 is -10. Then you move to the k, so plus k times, cross out the row and column that it's in, you get 4 minus 9 is -5. Now, if you don't like writing the i's, j's, and k's, then just change it to this, -5, 10, -5. But when you do the determinant, you have to have the I, J, K there, because that's going to give you the X, Y, and Z component. And that's how you compute the cross product. Compute a 3 by 3 determinant.
It doesn't matter which row you pick, right?
Yeah, but I like to go across the top because then you got the I, J, K there. But if you have a lot of zeros in there, you pick the one with the most zeros, right? Okay, now how do you use the cross product? Oh my gosh, I'm going to run out of time. We better not.
We got 18 minutes.
This is a crash course, that's why. So, because we still gotta do parametric equations. Okay. Oh, I erased it. Oh, got it. Okay, let's say you have 3 points. Okay, just read me the 3 points that we had from the last problem. What was A?
Write down the word.
You guys not even taking notes.
I am taking
I'm
notes,
taking
just,
notes.
I didn't write down the coordinates.
Okay, let's just make up some numbers then. 1, 3, 2. B is 4, 1, -1. And C is -1, -2, -4. Just make up numbers there. Okay, this triangle lies in a plane, right?
Yeah.
Write the equation of this plane. This is super important in multivariable calculus. How do you, okay, in 2 dimensions, what do you need to write an equation of a line?
AX.
No, what do you need
The
though?
slope.
You need the slope at a point, right?
Oh, same thing. with-
Now, in 3 dimensions,
Same.
what do you need to write an equation of a plane? I hope you guys know in 3 dimensions, the equation, see in 2 dimensions, ax plus by plus c equals 0. This is a line, right?
Yeah.
But in 3 dimensions, ay plus by, ax plus by plus cz plus d is gonna be a plane.
Yeah.
And then if you extend it to 4 dimensions, you get a hyperplane and so forth, yeah?
Don't you need like the
To write an equation of a
product?
plane, you need a point, and you need a vector that's perpendicular to the
So the
plane.
top.
Oh, normal, yeah.
Yeah, the normal vector. So that's the cross product. Because remember, the cross product is a vector perpendicular to the plane.
Top part.
So what you do is, you form 2 vectors, so you see these 3 points, form any 2 vectors you want. Why don't we go with AB and AC? So what is AB in component form? Quick. Head minus tail.
3, -2, -3.
Okay, what is vector AC in component form? Head minus tail.
-2, -5, -6.
Okay. Find the cross product of these 2 vectors. So you make a 3 by 3 determinant, I, J, K across the top. Now, since we're not interested in the direction so much, we just need a vector pointing that is perpendicular to the plane. So it doesn't matter which vector you put in first now. You guys understand that?
Yeah.
Because it doesn't matter if the vector points that way or that way, it's still
It's still
perpendicular, right? Okay, so this is equal to, see, this is how I do it. This is how the pros do it. You just do this first. See how you get the plus minus plus in. So you do this, cross out the row in the column that's in, 12 minus 15. And then this one, negative 18 minus 6. And then down, negative 15 minus 4. Oh, these are kind of ugly numbers. And if you want to put it back into this form, that's perfectly fine. There you go. So this vector is perpendicular to this plane right here. So therefore, the equation of the plane is going to be negative 3x plus 24y minus 19z plus d equals 0. The components of this perpendicular vector are simply the x, y, and z components. You guys know what I'm talking about? And then how do I figure out what this d is?
Plug in just like
Yeah, you plug in any one of these 3 points.
Wait, if that's the perpendicular vector, wouldn't
Yeah, the components of the vector are the coefficients of the plane.
but that's perpendicular to?
Yeah, that's the perpendicular vector. Okay, so that's how you write the equation of a plane. Okay, now find the area of this triangle.
Just find the length of each one.
Well, you can go 1/2 AB sine C, right?
Yeah.
Hey, but hey, isn't that the definition of the cross product?
Yeah.
Isn't the definition of the cross product
So it's half the
A,
cross
B, yeah, so it's, so the area of this triangle is simply half the length of the cross product.
And we just solve for.
So here's the cross product
We
right
just gotta
here.
find the length.
How do you find the length of it? Square root of this squared plus that squared, 576, plus 19 squared,
361.
which is 361. Divide that by 2, that's the area of the triangle.
946?
Okay, whatever it is, I'm just showing you how to get it. Okay, we got 10 minutes left. Now, how do you write the now this is a plane now. This is an equation of a plane.
Yeah.
How do you write the equation of a line? A line in 3 dimensions. For example, what if you have 2 points? Make up some numbers.
2,
Okay, 2,
3,
3,
5,
5. And then point B is
4,
4,
7, 11.
7, 11. Write the equation of this line, not a plane anymore, a line that goes through these 2 points. Well, whenever you write an equation of a line in 3 dimensions or higher, you got to do it parametrically. Okay, so the first thing you do is you write a vector that points in the direction of the line. And it can point any direction you want. So it can go from A to B or B to A. So let's just go A, B. Componentize. Head minus tail.
2, 4, 6.
2, 4, 6. Okay? Now watch. Watch what I do. Therefore, the equation of this line is going to be x equals
Oh.
2 plus 2t.
Yeah.
Y equals 3 plus 4t. Z is equal to 5 plus 6t. You see how that works? Notice that these numbers here correspond to that point. And then the coefficients of t are simply the components of the vector. But do you see how that works? What happens when you plug in 0 for t?
You get the original.
You get this point. What happens when you plug in 1 for t?
You get the next
You
one.
get that point. And then if you plug in 2 for t, you get another point over here, and so forth and so forth. And so that's how you get the line. And now, can you see there's an infinite number of ways of writing this now?
Yeah.
Because instead of using this point, 2, 3, 5, you could have used that point, 4, 7, 11. And that would be the same line, right?
You just do.
And what about this, 2, 4, 6? Could you have reduced that vector down to 1, 2, 3?
Mm-hmm.
Yeah, and could you have made it -1, -2, -3?
Yeah.
Yeah, so there's an infinite number of ways of writing an equation of a line parametrically, because it just depends what point you pick and what vector you pick, right? Because you can make any multiple of the vector. Okay, but what was our original one? 2 plus 2t, 3 plus 4t. Actually, this is dumb, because once you can reduce that, you should reduce it to make the number smaller, but that's okay, we'll just do it. What does the rectangular equation of this line look like?
Why don't you solve for?
Yeah, so what you do is you solve for t in this equation, what is t equal to?
T
Let's see if we can do it in our head.
half
X minus
one.
2 over 2. Solve for t in this equation.
Y minus 2
3
over 4.
And then solve for t in this
Z
equation.
minus 5 over 6.
Z minus 5 over 6. And then since t equals t equals t, you equate them. There you go. This is what the equation of a line looks like in 3 dimensions. This is called rectangular form.
It's all coming back now.
But then look, hey look, 2, 3, 5, that's the point. And then the 2, 4, 6, that's the components of the vector.
Yeah.
So again, there's an infinite number of ways of writing that, yeah?
Yeah.
Okay, last thing. What if I ask you, here's a line in space, okay? Where does the line intersect the plane? Okay, here's a plane. What's the equation? Somebody make, this is the plane, 3x plus 2y plus z equals
5.
5. Okay, just make up a number. Where does this line intersect that plane?
You plug in
Okay, let's
all
see.
the x and y and z.
Yeah, you just use the parametric form. You
You
use
solve
this. Now, if I were doing this problem, I would have reduced this vector down to 1, 2, 3, because then when you plug it into something, you get smaller numbers to work with, right? Yeah.
But just real quick, how can you just reduce it? Just
Because then it just takes longer.
all
time
you
to
need
get
is a
to
vector that points in the direction of the line. If this vector points in the direction of the line, then half of it points in the direction of the line too, right?
but you don't need magnitude. Doesn't matter.
No, you just need a vector pointing, or you can make it double as long, right?
Oh yeah, because this is we're still talking about that.
You just need
Like,
a
yeah,
vector
we're still
pointing in
talking
the
about-
direction of the line.
Got it.
Yeah, so that's why if you can reduce the vector, you should, because you get smaller numbers. Take these things, plug it into the equation of the plane, and so you get 3 times 2 plus t, plus 2 times 3 plus 2t, plus z, which is 5 plus 3t, equal 5. Solve this equation. 6 plus 3t, plus 6 plus 4t, plus 5 plus 3t, equal 5. Tuka, tuka, tuka. 10t is equal to
Negative 12.
negative 12. T is equal to negative 6/5. Once you figure out what t is, how do you figure out the coordinates of where it intersects the plane?
Plug it in.
Yeah, you plug it into this. Therefore, the coordinates of that point is, let's see if we can do that. Plug in negative 6/5 there. 4/5.
Is that 3/5.
3/5. And then
7/5.
yeah, 7/5. That's correct. There you go. Parametric form. Very useful.
They all tie into each other.
And then, okay, so you got a whole bunch of problems in that pack. You guys got the packet, yeah?
Okay.
The one on the website.
This one.
The one says vector review.
Ooh, lots of them.
I don't know. How many pages are there?
Lots of them.
Okay,
7.
7 pages?
And
Okay, we're gonna try and do it in. I don't know. You got. You're not gonna just do one a day now. It's
better
gonna,
do more than one a day.
yeah, it's gonna. You gotta try and finish all of these problems by hopefully what, next Tuesday?
Tuesday.
No,
Thursday.
next Thursday.
Next Thursday.
And then we
Okay,
can
got
take
a
the
week.
test on Friday.
Oh,
Well, let's just see where we are next Tuesday then, right?
oh,
So remember, we're gonna meet Tuesday, Thursday every week.
got it.
Tuesday, Thursday, and then test is either gonna be Monday, Wednesday, or Friday, whenever we finish.
We good then, Mr. Burke?